Last time in lab, you were introduced to the concept of feedback control for controlling the positioning of the slider servo. Last time, you learned about the most simple type of feedback control, which is called on-off control. In on-off control, we took a reading from the sensor, which was indicating the position of the slider, and we checked to see if the slider position was less than or greater than the position that we wanted the slider to be in. If the slider was less than the desired position, we turned the motor on in one direction, and if the slider was greater than the desired position, we turned the motor on in the other direction. In that lab, we learned about the concept of instability. When we first ran the on-off control, the motion of the slider was unstable. In other words, it kept oscillating back and forth around the desired position. We learned that there were some things we could do to improve the stability of the motion. One thing that we changed is we made the motor move slower. Another thing we changed is we made the loop time faster so that we checked the position of the sensor more frequently. The third thing we changed is we made the desired position have a greater range of where it could be and still turn the motors off. Another way of saying this is that we saw that we could improve the stability of the motion by making the motion slower or by making the motion less accurate. In today's lab, we're going to start out by getting a little bit more formal with these ideas of accuracy, stability, and speed. In order to understand the trade-off between stability, accuracy, and speed a little bit better, we'd like to start by looking at an actual plot of the sensor value as the slider moves to its target position. This will let us see what's happening more precisely than what we can see by just watching the motion of the slider with our eyes. Today, we're going to start by setting up the code in PSOC to look at the sensor value, and then we're going to write some code in MATLAB to plot the sensor value, and finally we're going to take a look at our circuit and make sure our circuit is correct, and then we're going to run a couple of experiments. So to start out with, open up your code from last time, the on-off control lab, if you have it, and go to your top design. In the top design, you should already have two PWMs, and you should also have an ADC block for reading the sensor. Your PWMs should be set up so that the prescaler is 1, the period is 100, and the compare value is 0. So make sure that you have this for both of your PWMs. For the ADC, you should have the VREF select set to VDDA. You should have your channels set to 1. The resolution should be 12 bits and the mode should be single. Then you should have 2 clocks wired to the PWMs. You should have 2 pins wired to the line outputs, and you should have an analog pin wired to the input of your ADC. If you have all these things, the next thing we need to do is we need to go to the communications menu and find the UART SCB mode block. Drag one of those to your screen and then double click on the UART and change the baud rate to 9600. We're going to set these settings for the UART to be the same as what we're going to use in MATLAB so that MATLAB can get values from the sensor. Now let's go and set the pins. You should already have the pins 1 and 2, which are the pins in the two PWMs. They should be connected to pins 1, 1 and pin 1, 2. And the pin reading the value from the sensor should be pin 2, 0. Then set your RX pin to pin 04 and set the TX pin for the UART to pin 05. On mine, they've defaulted to these values, but whether or not they default to that will depend upon what version of PSOC Creator you have. If they didn't default to 04 and 05, set them like that yourself now. Now let's go write some additional code in main.c. I have my code here set up like we had it last time in the on-off control lab. I've set my speed to 100 and I've set the delay to 1. Also, I have the range where the motor will stop to be between 1010 and 1035. So set those settings yourself now if those aren't the values that you have. Now, since we've added a UART to our top design, here in our code, we need to start the UART in order to be able to use it. The value that I want to send over the UART is the sensor value. However, this sensor value, if you remember, is a value that we declared as a 16-bit integer. But we can only send 8 bits at a time over the UART. So the first thing we need to do is to convert this one 16-bit value into 2 8-bit values. And I'm going to show you how to do that here. I'm going to create 2 new integers, and each of these is going to be an 8-bit value. And I'll make these be unsigned 8-bit values. And I'm going to call them top byte and bottom byte. So I have one 16-bit value and I want to break it up into 2 8-bit values. Finding the top byte is pretty easy. Here's how you do that. The top byte will be equal to the sensor value divided by 256. Now remember that the sensor value is a 12-bit signed value. So the sensor value can be anything between 0 and 2048. When I divide that value by 256, it might be a value that has a decimal. But because the sensor value is an integer and I'm dividing it by another integer, the way that the C language works is that the result of this division will also be an integer, and it will be the floor of this division. So in other words, if you take the sensor value and divide it by 256 and then just remove the values that come after the decimal place, that's what we'll get in top byte. And as it turns out, if we would look at what top byte is, it'll be a value that is itself somewhere between the value 0 and the value 255. So that will give us a top byte value that is only 8 bits. Now, I can also find the value of bottom byte. If I take the sensor value and I subtract what I got for top byte times 256, that will give me the remainder of this division as another 8-bit value. So in other words, I've just taken this one 16-bit value and split it up into two 8-bit values. When we receive these numbers on the other side in MATLAB, we can reconstruct the two values back into a single 16-bit value. So now that I have two 8-bit values, I can send them both over UART. And for that we use the command UART put char. Now there's one more thing I want to change before we're done writing this code. Instead of having this loop run infinitely many times as it is right now, I want to limit the number of times this for loop will run. And the reason I want to do that is because I now have these commands to send UART values to the computer, and I don't want to fill up the buffer on this UART communication. So if I left this so that it runs infinitely, we'll just keep sending values and fill up the buffer, and I don't want to do that. So let's limit the number of times this for loop will run. To do that, we'll go up to the top and we'll create an integer I. Then in this for loop, before the first semicolon, I say what I is going to be initially equal to. So we'll make I equal to 0 initially. Then, after the first semicolon, we'll put the condition for which the for loop will actually run. So I'll put I less than or equal to 600. So we'll continue running this loop as long as the value of I is less than or equal to 600. Finally, after the semicolon, I say what happens to I every time through the loop. And there's a little bit of a shorthand that we can use in the C language. I'm going to put I plus plus. And that means that every time through this for loop, I will increase in value by 1. So at the start of the for loop, I will be equal to 0. Every time we go through the loop, I will increase in value by 1, and the for loop will continue to run as long as I continues to be less than or equal to 600. So once we have all of this code in here, go ahead and build the code and check to see if you have any errors, but don't program the PSOC quite yet. I have a warning here that says control reaches end of non-void function. If you have a warning like that, don't worry about it. It's not an error and it won't impede the functioning of this code at all. If you have any errors, stop here and solve the errors that you have in your code before you move on. If you got here and you don't have any errors, we'll move on now and write some code in MATLAB. So go ahead and open MATLAB. I have MATLAB open here, and I have the command window, and I also have a script up here. So if you don't have a script window, click on New and click on New Script to get a script window to write some code. Note that you can tell the difference between a script window and your command window because the script window where you want to write your code, it has a line number. Here it says 1. Whereas in the command window, it has these little arrows next to it. So in our window here, we're going to start by opening a connection to the PSOC. If you have this code from previously, you can go and get that code that we had before. We would have done this last time, I think, in the read a potentiometer lab. This might have been when we did this last. So we're going to create a variable called sir_psoc for establishing a serial connection with the PSOC. So we'll use the function serial, which is a built-in function in MATLAB for creating a serial port. And then we need to put in the COM number for our PSOC. In my case, it's COM66, but you have to figure out what COM number corresponds to your PSOC. So to do that, first of all, make sure that your PSOC is plugged into your computer with the USB cable. And then, if you have a Windows machine, click on the Start menu and then click on Control Panel. When the Control Panel opens, search for Device Manager. Find the Device Manager and then go to Ports and expand your ports, and you're looking for a port that's called KitProg USB UART, and you want to note what number that is. Here mine is COM66. Whatever number you have there for COM, put that in right here in your MATLAB code. Then we have to set the settings for this serial connection. We need to set the baud rate. We're going to set that to 9600 because that's what we set for the serial connection in the PSOC. We need to say how many data bits we're going to be sending, and that will be 8, so it's a single byte. Then we need to set the parity. And some of these things you don't know what they are yet. If you take robotics 2, we do a session all about UART communication, and you'll learn what all these things mean. For now, we're just going to use it to learn about our control. So we also need to set the flow control, and here we'll set none. And after we've set all these settings, we need to open the sir_psoc connection. Now that we have the connection open, we can go ahead and read values from the PSOC. So we're going to use the same kind of a trick that we used in the PSOC to create a loop that will execute for 600 times. And here we're going to read a value rather than sending a value like we did from the PSOC. So while I is less than or equal to 600, note that this while loop is actually going to run one fewer times than the PSOC loop is going to run, because here we started the I out at 1, and it's still going to go while I is less than or equal to 600. We're doing this on purpose because if we would, say, lose 1 byte between the PSOC and MATLAB, we still want the MATLAB code to finish successfully. And if we would be off by even 1 byte, MATLAB would sit and wait for a byte to come until it times out, and we would get an error. So in order to prevent that from happening, we're going to make the MATLAB loop run 1 time fewer than our PSOC loop runs. So we're first going to read the top byte value. We use the function fread. We're going to read just 1 byte, and that's going to be an unsigned integer that is 8 bits. Then we're going to read the bottom byte, And then after we've read both the top and the bottom bytes, we're going to put the two values together. And we'll store it as value. So the way we put these two things together is we take the top byte and we're going to multiply that by 256, and then we'll add on the value of the bottom byte. And lastly, we'll increment the value of I and then end the loop. Now, after this loop has finished, we'll have a whole vector of values that have come from the PSOC, and we want to take a look at what all of those values look like. So we're going to create a figure, and we're going to plot value. So we should get a whole string of values that we have received from the PSOC over time. Then the last thing we need to do is we need to close SIR-PSOC, delete, and then clear. Now, note that it's very important every time you run this code that the code gets all the way to the bottom and executes these lines. If the code ever throws an error anywhere along the way so that it does not get to the point where it executes these values, what you want to do is before you run the code again, take these three lines and you copy them, hit Control-C if you have a Windows computer, and you want to paste them down here and then hit Enter to execute them. That way, these three lines will be executed in the case where you get an error before you get to these three lines. Now, in order to run this and see what happens, what you have to do always is run your MATLAB code first, and then as soon after that as you can, run the PSOC code to start that sending. When you run the MATLAB code, MATLAB will wait a little while to see if it gets a value, but it won't wait forever. So if you run the MATLAB code and then you wait too long to run your PSOC code, MATLAB will throw an error, and you have to do this thing where you copy these three lines and paste them down here and hit Enter. So before I actually go ahead and run anything, let's go and set up all of our circuitry. Now, you might already have this all set up from last time, and if you do, that's great. But take the time right now anyways to check through your circuit and make sure that everything's correct. So I'm going to take a couple minutes here and walk you through what connections you should have. Right now, since we're working with external voltages, and power supply, we have to be very careful to get our circuit correct before we actually plug in our external power supply, because we can damage our PSOC if we don't have things correct. So I'm going to take a moment and walk you through what we have. First of all, the chip connections should be like this. Make sure to start out by finding the top of your chip. Remember that the top of the chip is the part that has this indentation at the top. It's like a half circle and it's indented. Then the first pin on the left of the chip should be connected to VDD of your PSOC, and it should also be connected to the top pin on the right side of the chip. So you see I have a jumper wire here connecting the top two pins, and I also have a wire connecting this top pin on the left to VDD on my PSOC. Then pin number 2 is a pin that I have connected to one of the digital output pins on my PSOC. So pin number 2 for me is connected to pin 1, which is what I have selected in my PSOC code as one of the PWM pins. Then pin number 3 is connected to one of the 2 leads from the motor. Pins 4 and 5 are both ground pins. So one of these pins I have connected to ground from the power supply, and I also have one of those 2 pins connected to GND on the PSOC. So make sure you have a connection between either pin 4 or pin 5 of the chip going to GND of your PSOC. Then pin number 6 is going to the other lead of the motor. Pin number 7 is going to pin 1, 2 on the PSOC. That's the other digital output pin I have connected to the PWM. And then the last pin, pin number 8, is connected to the power of the external power supply, so the positive of the external power supply. Once you have all of those connections correct, and make sure after you've plugged in all these wires, have somebody else also double check the wiring. It's very easy to make mistakes in your wiring, and it can be difficult to find mistakes that you've made in wiring. Sometimes it can be much easier to find mistakes if you're not the person who actually did the wiring. So then go ahead and plug in your external power supply. And if your slider is not slid to one side, if it's somewhere else, slide the slider all the way to one side, because we want to be able to see how the slider moves from an extreme position to its target position, which right now is somewhere in the middle. So go ahead and slide your slider all the way. And we also have to make sure that the potentiometer is hooked up right now. So you have to find the 3 leads to the potentiometer, and once you identify which of those wires is the wiper, connect that wire to pin 20, and the other 2 wires you're going to connect to power and ground, or VDD and ground. So you want to connect these 2 to power from the PSOC, not your external power, and ground. Once you've got those, let's go ahead and give this a test. So in order to test this, the first thing you're going to do is run the MATLAB code. And in order to run it, you're going to have to give it a name to save it. And then as soon as you've got it running, run the PSOC code by clicking Program in PSOC Creator. So you see what happened was my slider shot to the center and it was a little unstable. It vibrated back and forth, and at the same time the MATLAB popped up a plot, our figure window. And this figure window doesn't have any units on the X and Y axes. The value on the X-axis is approximately milliseconds, because in our PSOC code we have a delay of 1 millisecond each time through the loop. On the Y-axis, this is the sensor value that's coming from the potentiometer. So you see what happened is we started at 0. Yours might have started at a maximum rather than starting at a minimum. That's okay. The slider shot towards its target position and it overshot. It went too far, and then it came back, overshot again, went back, and it kept vibrating until eventually it stopped vibrating and settled down. Now that we have this plot of the response of the slider, we can find some actual values talking about the speed, stability, and accuracy of the motion of our slider. The first value we're going to look at is an accuracy value that's called the steady state error. Now, if we look back at our PSOC code, we can see what sensor value we're trying to get the slider to go to. Here we have a range between 1010 and 1035. We have a range of about 25 sensor value units around our target value. So what that means is the position that we're trying to get the slider to go to is about 1022.5, which is exactly halfway between 1010 and 1035. Let's take a look at the position that the slider actually got to in its motion. I'm going to click on this zoom in button and I'm going to click and drag over the final value to zoom in. So there's some noise in the sensor reading, but it looks like the final value of the slider is about 1016. So if I take that actual final value or maybe it's like 116.5. So if I take 1016.5 and I subtract it from the position we're trying to get the slider to go to, which is 1022.5, I get a value of 6. In other words, the actual position that the slider stops on is a value of 6 away from where we're trying to get it to go to. That means that the steady state error is a value of 6. Now, we'd really like to have the steady state error value not in units of digital value, but in units of actual position. Can we convert the value 6 to an actual position? Let's write down what we know. We know that the target position was 1022.5, and we know that the actual final position was, we can find that from the MATLAB plot, was 1016.5. So that means that the final error is equal to 6. Now, we want to convert this to actual position. We know that the value of this sensor can range between 0 and 2048. And we know that the full range of the slider is about 4 inches. So if I take the 4 inches of the range and divide it by 2048, this gives me a conversion between inches and digital value. And what I get is that we have 0.00195 approximately inches per digital value. Now, if I multiply this by 6, this tells me in inches the amount of the final steady state error. Now, this is the amount of steady state error that we get with the conditions that we have set up. Our conditions include this range around which the motor stops, the speed at which the motor moved, the delay value down here, This is the amount of time that we wait from one loop to the next. And it's also a function of the type of control that we're using. So right now we're using on-off control. So we've found our steady state error. Let's see what else we can find. I'm going to zoom back out here. Let's look at another property we can get from this response. This response is called the time response, and we can use this plot to get other things besides the steady state error that we just found. Another value we can find from the time response is called the overshoot. Let's zoom in right here to get the overshoot. The overshoot is the difference between the value that we're trying to get the slider to go to and the maximum peak value that the slider overshoots to the first time it shoots past the target value. So remember, we're trying to get to 1022.5. Let's find out what this value is at the top of this peak. If I zoom way in, I find that this value is about 1139. So let's go find the actual overshoot. So here we already found the steady state error. Now let's find the overshoot. So our target value is 1022.5. And the maximum value that we reach here is 1139. I'm going to find the difference between these two values, and it is 116.5. Now I'm going to take this number and I'm going to express it as a percent of this number. So the way we do that is we go 116.5 is equal to something times 1022.5. So when I solve this, I get 0.1139, and that means that we have an overshoot of 11.39%. So now we've found steady state error, and we've also found overshoot. Let's find a couple more values. The next value we're going to look at is something called rise time. Rise time refers to how much time it takes for the slider to get from its starting position up to the first time it reaches the target value. So I'm going to zoom in here, and we'll first look at what time it starts here. We have a little bit of I have a little bit of strangeness at the beginning, but it starts at 0 at time 11, at 11 milliseconds. Now I want to find out at what time it first reaches our target value of 1022.5. Takes a little bit of finagling here to figure this out. It's right in there somewhere, so I'm going to zoom in a little bit more right in here. The amount of time, see, it reaches 1022.5 at about, there's 1022.5, at about 47.3 seconds. So if we go back to our calculations, let's find the rise time. It started at 11 milliseconds and it reached 1022.5 at 47.3 seconds, or milliseconds, that is. So the rise time, in my case, is 36.3 milliseconds. Now let's find one more value here. The last value that we're interested in is something called the settling time. This is the amount of time it takes from when it started its move until it stopped going back and forth. So I'm going to zoom in here. And it stopped going back and forth right around here. This isn't totally exactly accurate. We're just kind of approximating. So the settling time here, it stopped moving at about 2:35. So if I go back to the calculations, we've got 235 milliseconds minus the time it started moving, which was 11, and we get 224 milliseconds for the settling time. Now, the first value that we calculated, the steady state error, talks about the accuracy of the move. The overshoot is a value that talks about the stability of the move. The rise time is a value that talks about the speed of the move, and the settling time also talks about the speed, but it also kind of talks about the stability together. So what we're going to do now is we're going to do a little experiment to see how we can improve the motion. So go back to your code, and what I want you to do is make one of the changes that we learned about last time in class. So either change the speed or change the buffer around which we have the motor stop, or change this delay time. And then I want you to run the experiment again and calculate the overshoot, the steady state error, the settling time, and the rise time with your new change. So think about first what you would expect to happen. For example, if I would change this from 100 to 80, I would expect this to improve the stability of the move. So the overshoot should go down, but it should also make the move slower. So that means that the rise time should increase. Try this and do the calculations again and see what you get. If what you find out is not what you would expect, call me over and talk about it to see if you did something wrong. Once you have done this second experiment, upload the results from your experiment in the lab quiz for today.